Hello, everyone. Welcome to Pre-Lecture 8. This is going to continue our discussion of kinetics, talking about rate laws and half-lives. This pre-lecture is brought to you by the periodic table. Do you need a new table? Make it periodic. Check out our sponsor after this video. Okay, so thus far in class, we've discussed rate laws and rate equations. These are essentially mathematical expressions that describe how our concentration of a chemical during a reaction will change over time. Simply put, that's what kinetics is. If we have some sort of reaction where we have some stoichiometric coefficient of A, represented by lowercase a here, plus B will form some products, we can write a rate law for that. So a common thing that you'll see for every kind of rate law is rate is equal to, and so our left side of the equation will always be rate. There will always be a rate constant, which is this lowercase k, and that is going to be temperature specific for a particular reaction. And so that would, of course, be given to you, or you would be able to solve for it with information given to you. And then we have our different chemicals, A and B, and they are raised to some power that we call M and N. And so M and N have to be experimentally determined. And those are what we would call the reaction orders. And so generally, a reaction order is usually 0, 1, or 2. And this is something that must be determined experimentally. It's not something we can come up with by theory. We actually have to run an experiment, okay? And so the overall reaction order then, say for example, M was 1 and N was 2, then our overall reaction order would be the sum of those, which would be 3, but the reaction order for A would be 1, reaction order for B would be 2, okay? Let's talk a little bit more about K here. And anytime we have, let me go back, anytime we have our rate, the units on that are always going to be equal to molar per second. So concentration over time, right? And so that's what our units say there. And so our units of K then ultimately the units on K are determined by what we need to do in order to get the units for the overall reaction to be molar per second. And so a reminder that we're taking K and multiplying it by concentrations raised to some power. And so in your textbook, there's a table if you would like to memorize it. Just a reminder again that molarity is moles over liters. So anytime you see moles over liters, that is what molarity means, right? And so if we have a 0 order reaction, then in order to get our units on the left side of our equation, our rate to equal molarity per second, we would just need to have our units on K be molarity per second, right? If our reaction is first order, that would mean K is going to be multiplied by a single chemical with a exponent of 1, meaning that it's going to be just a concentration in molarity. And so if we already have a concentration in molarity, our units on K will be per second. So this negative exponent means that it is 1 over seconds. And so that would be our first order. Then you can also see second order and third order, okay? Right, we also have integrated rate laws. And so these relate to the rates of concentrations and reactants. We can get a second form of each of these rate laws that is integrated. And so this can essentially be used to determine the amount of reactant or product present at any period of time and estimate time required for a reaction to proceed to a certain extent. And so as you might guess by the name, the integrated part of integrated rate laws comes from calculus, which we won't be doing in general chemistry, but just wanted to give you a little background there as to how we actually get these integrated rate laws. And so with that, our first order integrated rate law. So again, for a first order rate law that is not integrated, we have our rate is equal to K, our constant, times some chemical, some reactant, A, and its concentration, okay? And so if we integrate that, it turns into this expression where we have the concentration of our reactant A at any time is going to be equal to the initial concentration times E. This is our mathematical constant E, raised to the negative KT. And so again, K is the same K here, and T is time. Okay, and often that time is in seconds, but it can be in any units really. Okay. And so this can be super powerful then if we graph the relationship between the concentration of some reactant. In this case, we have hydrogen peroxide, H2O2. If we take the natural log of that and graph it against time, then we should get a straight line relationship if this reaction is first order. And so essentially we get a y equals mx plus b relationship, and this is just a rearranged form of this integrated rate law. Okay, so that is first order. For second order, in this case, again, we have our rate being equal to some constant and then some chemical reactant squared. So if we integrate that, we get this as our integrated rate law, where we have the inverse, or 1 over our chemical at any time, being equal to kT plus 1 over the initial concentration of that chemical. Okay, and then graphically, we can also represent this where we should get a straight line with a positive slope. If we were to graph this as 1 over the concentration of our chemical versus time, if we were to graph it with the natural log of our chemical versus time, we would get a curved line. Okay, so that's a key thing we're looking for when we're graphing something in order to determine the rate law, is what sort of equation gives us a straight line. Okay. Finally, we have 0th order rate laws. And so in this case, we just have rate is equal to K. It is not dependent on the concentration of our reactant. And so if we integrate it, this is our integrated rate law shown right here. And if we were to graph it as just the concentration of our chemical versus time, if it is 0 order, we would get this top example. So this would be the decomposition of our chemical ammonia on tungsten, which is W, that's its chemical symbol. If it is not first order, then we would get a curve, or not 0th order, pardon, we would get a curved line. And so that would be representative of the decomposition on SiO2. Okay. So again, these are just defining what these are and then saying what I already said. So there you go. Okay, that's going to be our integrated rate laws. We're going to talk about half-lives in class. Hope that was informative. If you have questions, please let me know. Otherwise, I will see you in class on Thursday.